In this presentation, we will continue our discussion on functional groups. So for this presentation, we will be looking specifically at the functional groups amines. Then we will look at aldehydes, followed by ketones and carboxylic acids, esters, and amides. It seems like a lot, but we'll just basically introduce these functional groups here. First, the amines. The amines, as we mentioned earlier, they have carbon and hydrogens, and of course the heteroatom nitrogen. So once an organic compound has N in it, one functional group or one type functional group that it can be is an amine. Let's look at these carefully. If N is bonded to 1, 2, and 3 hydrogens, it's ammonia. Remember that nitrogen has 3 bonds to it, compared to carbon that has 4 bonds. Here's another type amine. The nitrogen is here, but notice it now has 1, 2 hydrogens, and 1 carbon alkyl group. Since it has just 1 carbon alkyl group, it is classified as a primary amine. Notice 1 superscript 0. Another classification of amine can be, here's the nitrogen, and if it's bonded to 1, 2 carbon containing groups, and of course a hydrogen because it needs 3 bonds, it's a secondary amine. And the last category of amine is, as you can imagine, it's a tertiary amine, where the nitrogen is bonded to 1, 2, and 3 carbon containing groups that we'll call R or alkyl groups. So you should be able to classify amines as primary, secondary, or tertiary. Here's another way of looking at it with some specific examples here. This is methylamine. It's classified as a primary amine. Why? Because here we have NH2 and it's bonded to 1 alkyl group. Dimethylamine is a secondary because it has 1 hydrogen and 2 methyl groups. So again, you have to look carefully at how it can be written. It can be drawn out like this in the structural manner, or it can be written like this in the condensed manner, where this 2 here makes reference to 2 methyl groups. Let's look at this one. Here's a nitrogen, and it has 1 methyl, 2 methyl groups, 3 methyl groups. Therefore, it's a tertiary amine. So we can write this as trimethylamine, and the structure can be shown with N bonded to 1, 2, and 3 methyl groups, or we can put CH3 and 3 to show that there are 3 that's bonded to this nitrogen. Let us look at some applications and properties. Amines have a pungent odor. Once you open a bottle of amine in the chemistry lab, you know that an amine is present. But they are of biological importance. Here's one, Novocaine. I hope you can recognize the amine. Here's a nitrogen, and it's bonded to 2, 3, and 3 groups. So that's 1, 2, and all of this is a third group, so this is a tertiary amine. Here is another amine here. Notice that this is bonded to, this nitrogen is bonded to 2 hydrogens and a group here, so therefore that is a primary amine. Histamine, here's the amine, and that's a primary amine. We won't discuss this type amine as yet because it has double bonds to it. And here's another one, dopamine. Here is the amine, and it is a primary amine. Let's look at this one. These two have been in the news recently, and that's chloroquine and hydroxychloroquine. Here's a nitrogen, and you should be able to classify that as a primary, secondary, or tertiary amine. I hope you can tell that it is a tertiary amine because it's bonded to 3 alkyl groups and no hydrogen. Here's another nitrogen. That means it's amine, another amine functionality. And of course you can see that is a secondary amine. Hydroxychloroquine here it differs because it has the OH group. But here is the amine, and here is the amine, and of course that's a secondary amine, and this is a primary amine. So you should be able to look at organic molecules, identify the functional groups, and if you have identified an amine, you should be able to tell if it is a primary, secondary, or tertiary amine. Let us apply what we've just learned. So here's a problem. Draw the condensed structural formula. Now it's the condensed structural formula. You will have to show how bonds are connected to atoms, or how atoms are connected to different atoms through bonds. So here's the molecular formula. C3H9N. Hint. Remember that carbon has 4 bonds to it and nitrogen has 3. So whenever you draw your structure, you must have 4 bonds to each carbon and 3 bonds to the nitrogen. There's only 1 nitrogen here. Let us see the answer. So, as you can see here, it's possible to have a carbon bonded to a carbon, bonded to a carbon, that's 3 carbons, and that's bonded to your amine functional group. That structure is not complete. It's just a matter of getting your reasoning intact. Here's another possibility. 1, 2, and 3 carbons, because there are 3 carbons in this molecule, but this amine functionality can be bonded to this carbon here compared to bonding to this carbon here. So to make it a complete structure, we'll have to put in the 9 hydrogens. So here is where you have to be extremely careful to make sure that there are 4 bonds to carbon and 3 bonds to nitrogen. Putting in the hydrogens on this carbon means we have 3 hydrogens. So we have 3 hydrogens, and the 4th bond, of course, is to carbon. We have 2 hydrogens to the carbon in the middle, and we have 2 hydrogens bonded to the carbon in the middle. So this would be a complete structure, one of the structures of an amine that has this molecular formula. Here's the other one. This carbon here has 3 hydrogens because there are 4 bonds to a carbon. This carbon, however, since there are 4 bonds, it will have 1 bond here to the amine, 1 bond to the methyl, and we'll have to put in just 1 hydrogen here because the other bond is to the methyl group. So that is another possibility of a molecule or an amine that has that molecular formula. Okay, let us look now on a different type functional group. This one is called the aldehyde. And we'll combine studies here with the aldehydes and ketones because they are very similar in structure. Notice similar, not the same. Why do I say they are similar? Because both have the carbon-oxygen double bond. Both the aldehyde and the ketone have the carbon-oxygen double bond. That's called a carbonyl group. So here we have an R group that can bond here and another R group that can bond here. If we have two hydrogens, that is a specific molecule, and that's called formaldehyde. If we have here a hydrogen bonded to the carbon of the carbon-oxygen double bond, this becomes an aldehyde, and then we can add different alkyl groups to that carbon. So notice this entire group here is now the aldehyde. A ketone differs from an aldehyde because we have now replaced this hydrogen with an alkyl group. So a ketone has two alkyl groups that are bonded to the carbon of the carbon-oxygen double bond, and that's a ketone. Subtle difference, but they are two different functionalities. Let's see if we can look at it a little differently. Here is an aldehyde, R. This is the R group back here. This is the carbonyl, and notice it's bonded to a hydrogen. That makes it an aldehyde. Here's another example. Aldehyde functionality is here. So the hydrogen that's bonded to the carbon of the carbon-oxygen double bond makes this molecule an aldehyde. A ketone, on the other hand, has two alkyl groups bonded to the carbon of the carbonyl or the carbon-oxygen double bond. No hydrogen that's bonded directly to the carbon. So this is a ketone. Here's an example of a ketone, and as you know, this is acetone, a common organic solvent. So these two molecules are different. This molecule is different from this molecule because this is an aldehyde and this is a ketone. Here are some examples of aldehydes and ketones. This is an aldehyde, and it's vanillin, which is a vanilla flavor. Carvone, which is spearmint flavor, is a ketone. That's a ketone because there are no hydrogens that's bonded to the carbon of the carbon-oxygen double bond. Cinnamaldehyde, cinnamon flavor, is an aldehyde because here's a hydrogen that's bonded to the carbon of the carbon-oxygen double bond. So this molecule here is an aldehyde, or it has an aldehyde functionality. Benzaldehyde, another molecule, is an aldehyde because here is the aldehyde functionality, or benzaldehyde has an aldehyde functionality. So here is a question or problem to see if we can apply that knowledge. So the question now is to draw a condensed formula for two aldehydes. Notice aldehydes with the formula C4H8O. Careful, so this has an oxygen and we're looking for aldehydes. Again, we must ensure that carbon has 4 bonds, and in this case, since we have oxygen and not nitrogen, oxygen has a maximum of 2 bonds. Not 3, not 4, 2 bonds. So let's see if we can apply this concept here. So here is one possibility. We have carbon, 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 carbon. So that makes 4 carbons. We have the aldehyde functionality, and here is the aldehyde functionality. So notice we have used up here 1 hydrogen. So we have 7 that we need to bond back here to make sure that carbon has 4 bonds and oxygen has 2. Here are the 2 bonds. It's a double bond. Another way of writing the same molecule is CH3 bonded to CH2, bonded to CH2, and here is the aldehyde functionality, same as this. There's another possibility though, which is a different molecule. So we can put carbon bonded to another carbon here, and here is the aldehyde functionality. So you should always be looking out for possibilities. And that's why organic chemistry is such an important subject, because it builds your sense of observation and critical thinking. You should be thinking, are there any other possibilities with this formula here, and we'll end up having the same aldehyde functionality. And here is another possibility. So this molecule here is different from this molecule because the bondings are different. But both have the carbonyl or the aldehyde functionality right here. So they're 2 different molecules. Let us look at another possibility here. So draw condensed formulas for 2 ketones with the molecular formula C4H8. So let us remind us again that carbon has 4 bonds to it and oxygen has 2. You'll see, well, let's see what we can do here. So what happens here is that we have, this is our carbonyl or our carbon oxygen double bond. So this uses up 1 carbon here and 1 oxygen right here. So we have 3 more. We need to put 1 carbon on this side and another alkyl group over here. So now you've seen that we have used up our 4 carbons. So this is the ketone here with the molecular formula this. Note, however, that this is the only ketone. So this wording is not technically correct because this is the only ketone. If we put the carbonyl here, it would be the same molecule. Give it a try. So the answer here is they are not structural formulas that are possible, but just one that's possible with this molecular formula. Okay, let's turn our attention now to a different functional group, and this one is the carboxylic acid. Carboxylic acids. So let's first of all identify the carboxylic acids and look at some examples. So here is the functional group carbon oxygen double bond, carbonyl, as we can see here. But in this case, it's bonded to an OH group, hydroxyl group. So there's a direct bond from the OH group to the carbon of the carbon oxygen double bond. Here's a specific example, acetic acid. Of course, as we know, that's a major ingredient in vinegar. So here we have the carbon oxygen double bond and an OH bonded to it. And here's the alkyl group. So that's a carboxylic acid. Let's look at another representation of this. So we have here the carbon oxygen double bond, and we have the OH group that's bonded to this carbon. Another way of writing it is like this: OH group bonded to this carbon. Another way of writing it that you'll often see is COOH in a straight line. The assumption here is, as chemists, we know that this oxygen, this CO, is this carbon-oxygen double bond, and this OH here is bonded to that carbon. Another way of writing this is RCO2. So we take these two oxygens here and we just put a subscript 2 to show that there are two oxygens, and of course here's a hydrogen. So these are all ways of representing carboxylic acids. So look out for that. There are different ways of writing the functional group carboxylic acid. Let's look at some examples here. Naproxen, which is used as a painkiller or treatment for arthritis. Here is a carboxylic acid. So that molecule has a carboxylic acid functionality. Ibuprofen, a painkiller that we take whenever we have headaches, etc. It is a carboxylic acid just based on COOH. As I mentioned earlier, acetic acid found in vinegar. Here is the carboxylic acid functionality. And of course, aspirin, here's the molecule. This is a carboxylic acid. So look out for different ways of writing the carboxylic acid functionality. Here's one, here is another, and here's another. Notice this group here is not a carboxylic acid functionality. We'll see later on it's an ester. So be able to recognize, so observe carefully so you can recognize the COOH as your carboxylic acid functionality. Let's see if we can do this. Draw a condensed structural formula for a single carboxylic acid with this molecular formula. So notice the molecular formula does not give you an idea of the structure of the functional groups or the structure of the molecule. It just tells you how many atoms and are in that particular molecule. So once again, we have to ensure that carbon has 4 bonds whenever we draw out the structure, and we have to ensure that oxygen has a maximum of 2 bonds whenever we draw out the structure. Notice that this molecular formula here does not tell you how these atoms are bonded together. As organic chemists, we need to know how these atoms are bonded together to form the molecule. Because when we start doing the reactions, we'll have to visualize the structure, the actual structure of the molecule. So let us look at the answer. So here we have a carboxylic acid. We know it's a carboxylic acid, so we know we will have to put this in there. That has to be obvious. And of course, this takes up one of the carbons from this formula and one of the hydrogens from this formula. So now we have just 2 carbons to distribute and of course 5 hydrogens. So once you have introduced this, just bond it to 2 carbons to get 3 and include the hydrogens so that each carbon has 4 bonds to it. So this is the structural formula of the molecule with C3H6O2. Another way of writing it is like that. So again, look out for the different ways of writing functional groups. It could be COOH or drawn out like that. Let us look here at another functional group. We call these esters, esters of carboxylic acids. Esters have a characteristic aroma, and they're used specifically as flavors and perfume. in the cosmetic industry. They're also used as solvents. But let's look at the functional group of esters. It again contains the carbon-oxygen double bond right here. But the difference is bonded to this carbon of the carbon-oxygen double bond. It's not a hydrogen, it's not an OH, but it's an OR. An OR that's bonded to it. This is another carbon alkyl group. So you'll have to look out for, again, different ways of writing that. Here's one way, R, C, double bond O, OR. Notice it's OR, where R here represents a carbon containing group. We could write it like this, RCOOR. And as you can imagine, since there are two oxygens here, we can just write RCO2Rs. So be on the lookout for different ways of writing the ester functionalities. Let's look here at another representation of the ester group. So here's the ester group right here. And we can bond it to a carbon or another carbon back here. A specific one here is methyl acetate. Here is the ester functionality, and it's bonded to a carbon R group and a carbon R group back here. So let me be a little more specific. So this carbon R group is bonded to the carbon of the carbon oxygen double bond, and this carbon R group is bonded to the oxygen of the ester functionality. So be on the lookout for that. Here is another way of writing it. It's a little more condensed, but it's essentially communicating the same features as over here, COOH. Let's look at some practical examples here. As I mentioned, esters are used as flavoring in the flavoring industry a lot. So this is one that's pretty common, isoamyl acetate. Don't worry too much about the name. We'll learn to name these molecules later on. But just be able to identify the different functional groups that are in different molecules. So this molecule has the aroma of banana. So it really smells like banana. And it's an ester because of this right here. Orange aroma is right here. Notice that these molecules are different because they have different numbers of carbons and hydrogens. So these lines here really represent carbons and hydrogens. We'll say more about that in the next chapter. But the bottom line is this molecule here is an ester, or it has an ester functionality, and of course it has the aroma of pineapple. Okay, let's turn our attention now to another functional group called the amides. So this functional group here has, again, as you can see here, the carbon-oxygen double bond. You can tell that's a very important feature in organic molecules. But in this case, it's not bonded to a hydrogen. It's not bonded to another alkyl group, carbon containing. It's not bonded to an OH, as in carboxylic acids, and it's not bonded to an OR alkyl group, as an ester, but it's bonded to a nitrogen. So that makes it an amide functional group. Since, of course, as you know, amides, nitrogen has 3 bonds to it, so it can be in the form of hydrogens or hydrogens. In this case, it's a primary amide. It's an amide, first of all, because of this feature right here, and primary because it only has 1 alkyl group bonded to this nitrogen, or 2 hydrogens. This one is a secondary amide. First of all, it's an amide because of this feature right here. It's secondary because it has one alkyl group and two groups bonded to that nitrogen. So it's a secondary amide. This molecule here is a tertiary amide. Tertiary because this nitrogen here has 1, 2, and 3 groups bonded to that nitrogen, but it's also an amide because it has that feature to it, so it's described as a tertiary amide. So you should be able to look at an amide and tell if it's a primary amide, a secondary amide, or a tertiary amide. Here are some examples. So this molecule here is acetamide. You can tell it's an amide because this is the carbon-oxygen double bond bonded to a nitrogen. This nitrogen here has 2 hydrogens, so it is a primary amide because only one alkyl group or carbon group is bonded to that nitrogen. This is a secondary amide because here is the amide functional group right here, carbon, oxygen, nitrogen, and bonded to this nitrogen is a methyl group and this alkyl group here. All of this. That makes it a secondary amide. Of course, there are 3 bonds to nitrogen, so therefore we'll have to put a third, which is hydrogen. And here's another one, N-dimethyl formamide, very common solvent in organic chemistry. And notice it's an amide again because of right here. It's tertiary because this nitrogen here is bonded to 2 methyl groups and a third group back here, so therefore that nitrogen has 3 bonds to it that are not hydrogens, so therefore it becomes a tertiary and an amide because of the amide functionality. So again, you should be able to recognize amides as functional groups, and you should be able to classify amides as primary, secondary, or tertiary. Here is a very important application of the amide bond. As you can see, here is the amide bond here. Here's the carbonyl or the carbon-oxygen double bond that's bonded to nitrogen. So this is a very important bond, especially in biology, because it's also called the peptide bond, or the amide bond is also called the peptide bond in biology, and it essentially links 2 amino acids, here's one and here's another one, to form a dipeptide. But the main aspect here is this is the amide bond, which is also called a peptide bond in biology, which is used to bond 2 amino acids to form peptides. As you can imagine, a longer peptide would have many peptide bonds to it. So in conclusion, let us see if we can apply what we have learned here. So here's a molecule. It looks like a huge, well, it is a huge molecule. It's called Taxol, and Taxol is used in the cure for cervical cancer. So you can see it's a very large molecule, but equally important is it has many different functional groups. So on a test question, what I would give you is a molecule like this and ask you to circle the different functional groups and name them. So let us see if we can do a few. Here is an amide bond, because this is the carbon-oxygen bonded to a nitrogen. So that's an amide. We can classify that even further and say that this is a secondary amide bond because this nitrogen is bonded to this group here, and just has just one hydrogen. Here is an ester, because it's bonded to an alkyl group here and another alkyl group over here. Let's see if we can identify another one. Here is a ketone. Notice it is not an aldehyde because there are no hydrogens bonded to the carbon of the carbon-oxygen double bond. As a review, we did this earlier. Here is a alcohol, and you should be able to classify that as a primary, secondary, or tertiary alcohol. And remember that classification is based on the number of groups bonded to this carbon, the carbon that contains the OH. So that's a secondary alcohol because it has two groups bonded to that carbon. There's a hydrogen here that's not shown. Now the alcohol is right here. Don't worry too much about the dashed and the wedged lines. We'll say more about that. But for the time being, they are just lines that are used to indicate bonding. And see. So this is, I think this is the end of chapter 10, and yes it is. So what we need to do here is to be able to identify the functional groups that were discussed in this chapter. You should be able to look at a molecule such as Taxol, and you should be able to identify the functional groups and give the names of the functional groups. Okay, so once again, continue to study hard. As I said, we won't have a quiz this Thursday, but we'll have one the following Thursday, which will be on this material. So continue studying hard, and I'll post the PowerPoints on the on D2L. So all the best, and bye.